Okay, welcome everyone to our second evening presentation in Australia. Okay, so it's a great pleasure this week to welcome Alex Smits back to Melbourne from Princeton University, albeit only virtually. Professor Smits is going to tell us all about measurements in wall-bounded turbulence. Over to you, Lex.
Oh, thanks, Phil. I'm sorry that you're not seeing my face. There has been a little bit of a problem with the Zoom connection, but the most important thing's on the screen. I hope that you will see what I see. And thanks, Phil and Özge, for the invitation. It's a great pleasure to be able to talk to this group. My topic is measurements in wall-bounded turbulence, and I'll explain what I mean by that and what I'm trying to draw out in a way as I go along. But before I do that, I should thank the sponsors that I've had. Is the National Science Foundation, the Office of Naval Research. They've been especially helpful. AFOSR and NASA. All these people, these funding institutions have supported my work in the past, and I'm very grateful for it. Couldn't have happened without them. So let me begin. What I have, sorry, it's a bit slow. There we go. All right, sorry. I'm going to be talking about canonical wall-bounded flows, and what I mean by that is there are three versions of that. There's a fully developed channel flow at high aspect ratio, a characteristic dimension half height h, a fully developed pipe flow with a characteristic dimension the radius, and boundary layers on flat plate zero pressure gradient flows with a characteristic dimension delta. And all these flows, I'm assuming they're fully turbulent, high Reynolds number, and free of history effects. So the talk that with respect to these canonical wall-bounded flows, I want to show how advances in experimental techniques and computation have been vital to improving our understanding of these flows. And I'll do that by using three examples: Reynolds number scaling on the mean flow, Reynolds number scaling on the turbulence, and then also to talk about Mach number scaling, so to talk about the behavior of supersonic and hypersonic boundary layers. So just to get started, there's some notation that I'll be using. This is for boundary layer delta. The wall distance is y, and I'm particularly going to talk about the streamwise velocity behavior, and so that will have a mean value and a fluctuating value. And I will non-dimensionalize this, and that will be signaled by the plus sign. So, for example, the non-dimensional velocity will be the velocity divided by the friction velocity u tau, and u tau is defined on the basis of the wall stress. If you take the shear stress at the wall and divide it by the density of the wall, you get a velocity squared. And so this gives us a convenient velocity scale for non-dimensionalization. And that's also done for the streamwise turbulence intensity u squared plus bar. So that's our terminology. Now, when we think about what we've learned or what we know, I've sort of framed this in terms of some questions like, what did we know or did we think we know for incompressible boundary layers and other wall-bounded flows? Well, the first things that we always say is that far from the surface, the motions scale with the flow thickness, the shear layer thickness, delta R or H. And in the picture on the right by Cantwell, Coles and Dimitakis, if you look at the top view, that's a side view of the boundary layer. And we see these large billowing motions away from the surface, and those are the outer layer motions that we would expect to scale with the boundary layer thickness. And then conversely, if we look at the flow near the wall, the picture below is the streaky structure is looking up through the boundary layer from the bottom. So it's a plan view looking up into the boundary layer, and we see these streaky structures with a characteristic dimension of about 100 viscous length scales, and that Ayton knew that viscous length scale is defined as the kinematic viscosity of the fluid at the wall divided by the friction velocity. That gives us a length scale. And 3 or 4 of those length scales near the wall would be similar to the Kolmogorov length scale. So there's this relationship. It sort of represents the smallest motions that you would see in a turbulent flow. So it seems that near the wall, we can use that viscous length scale as the scaling parameter. Far from the surface, we use delta. And then if we take the ratio of those 2 length scales, we end up with what's called a friction Reynolds number, delta over eta W, and that gives a delta U tau over nu W. That's our friction Reynolds number, and that's the Reynolds number I'll use throughout this, this presentation. If so, what do we expect about the mean flow? Well, there's a sort of turbulent bedrock called the log law. So it's argued that if you go to a high enough Reynolds number, there is a region that of overlap between the inner and outer length scales. And in that region, the only length scale that can happen is the distance from the wall. And so by doing this overlap argument, dimensional analysis, like Millikan proposed, and you match the velocity gradients in the overlap region, you get this expression that the velocity gradient is u tau over kappa y, where kappa is von Karman's constant. So this is a result of the overlap argument on the velocity gradient. You integrate this, you get the log law. I show some results on the right from 1932, Nicorazzi's pipe flow, and it looks pretty well like the log law is present. So what is new about this? We've been around, you know, we've known this for a long time. Is there anything new to be found at all? Well, there's been a reasonable amount of controversy or uncertainty about the value of the slope of that line, kappa, von Karman's constant. And it's a good question to ask also, where does the log law begin and where does it end? So if we wanted to answer those questions, we must have a very high Reynolds number. We need accurate measurements of the velocity, and we need accurate measurements of the friction velocity or the shear stress at the wall. So, all right, first things first, we need a high enough Reynolds number. And to do that, we really needed to build some special facilities because we wanted high Reynolds number under laboratory conditions so we can take accurate measurements, very controlled conditions. And in Princeton, we chose the idea of using high pressure as the working fluid, and that would give us very high Reynolds numbers in a relatively modest size facility. And so you see on the left is that blue facility, that's the high Reynolds number test facility. That's mainly a boundary layer facility. And on the right, we see the Superpipe, the green one, where we have taken mean and turbulence measurements. And the Reynolds numbers we can get from 1,000 to 100,000 for turbulence measurements. For mean flow, we can actually go up to 500,000 for the Reynolds number. So we have a huge Reynolds number range to explore pipe flow. The other facility on the top right is the high Reynolds number boundary layer wind tunnel at Melbourne with Ivan Marusik. That's an atmospheric pressure tunnel, and they get high Reynolds numbers by making it very large. So as a very long working section, 27 meters long, you get boundary layer thicknesses of about 30 centimeters, and so you get high Reynolds number. And I should also mention that the other one, that the facility at Stanford by De Graaf and Eaton, it also uses high pressure, but up to 8 bar, not 200. But still, they put a wind tunnel inside and you get Reynolds numbers on a boundary layer of about 10,000. So these are purpose-built facilities for exploring Reynolds number effects. So here are some results that we got in 1998, more than 20 years ago. But what was surprising about that is, see, and this is the problem when you ask questions sometimes you get surprising answers you didn't expect. And the unexpected result here is that the log law doesn't actually start until some considerable distance away from the wall. For y plus less than about 600, y plus is the non-dimensional wall distance, yu tau over nu, less than 600, we actually see a power law rather than a log law. And that power law, if you see it, it's almost the 1/7 power law. It's a constant times y plus to the 0.142, so that's almost 1/7. And that fits the data rather better than the log law. And we couldn't have seen that without paying great attention to the accuracy of the measurements, because otherwise this would just get lost in the experimental uncertainty. So for pipe flow now, instead of beginning at like 30 or 70 y plus, as you might read in textbooks, even modern textbooks, it really doesn't start until about 600. And for this case, textbooks are also uncertain about where they end, either 0.1 to 0.3, depending on where you go. This one ends at 0.12. Now, one result is that it means that if you wanted a region of y plus of 1 octave, and then the log law is only going to show up for Reynolds numbers greater than 10,000. So that sort of emphasizes the need for very high Reynolds numbers. And what about the value kappa, the slope of that line? Well, you see on the graph, it shows it as 0.421, and that was our original conclusion. But we kept doing the same experiment over and over again. And every time we did it, we got a slightly different result. And in 2014, we said, look, we really don't know kappa better than 0.40 plus or minus 0.02. And this is in a facility where we've taken extraordinary care to get accurate measurements and repeatability and so on. And yet this is the best that we can do. And now other people find more precise values. And so I tend to disagree with that, because we've tried our darndest in the best possible facility for measuring this, and we have this kind of level of uncertainty. So another question, can DNS help? Well, if we look at some DNS results, this is from the channel flow by Lee and Moser, maximum Reynolds number of 5,200. There's the indicator function on the left there, and you can see that if there is a log law, then there should be a plateau. That black line is the highest Reynolds number case. The sort of purple line is that plateau, and that should be at a value of 1/kappa. Now you can see that, yes, there is a kind of an inflection point in that curve, but I wouldn't describe it as a plateau. And in fact, if you take the data from the channel flow and plot it, as I did on the right, in log-log coordinates, so you'd see power laws, you see that the velocity profiles in the channel flow really follow that power law we found for the channel flow, that sort of almost 1/7 power law that I showed earlier. And so the conclusion here really is the Reynolds number for this DNS is not high enough to show a log law in the mean velocity profile. What about turbulence? Here we have some expectations as well. The first expectation is that the Townsend-Perry attached eddy model predicts the intensity distributions in the overlap region. And it gives it this logarithmic behavior, B1 minus A1 log to the y over delta. And there is a Vy is a correction term, a viscous correction term that should go to 0 as the Reynolds number goes to infinity. Now, this idea was based on Townsend's proposal of the attached eddy, which, quoting here, the velocity fields are the main eddies, which he means the stress-bearing eddies that are sort of identified with the overlap region, regarded as persistent organized flow patterns, extend to the wall, and in a sense they are attached to the wall. So they scale with the distance from the wall, and following that argument will give you this logarithmic intensity distribution. Now, to show this log law experimentally, we know we need high Reynolds numbers, because experiments up to RE plus of 5,000 failed to show the presence of this log law or any extended region of it, so that you could actually find out what the slope was, for example, what A1 was. So we have the high Reynolds number facilities now, but we need better measurements. Measurements were done with hot wires. Hot wires have you can only make them so small, so they have spatial resolution problems. And so we felt the need to develop much smaller probes, and these are called Nano-Scale thermal anemometry probes, NSTAPs. And by using MEMS construction, we're able to develop these probes that have a freestanding platinum ribbon. It's not really a wire, it's a ribbon. It's 100 nanometers thick. It's 2 micrometers wide, and the lengths we can make are either 30 or 60 microns sensing length. We've used the 30 micron for the results that I show here. And given that it's very short, we have good spatial resolution, and also because of its very low thermal inertia, we have a very high frequency response. So we're very pleased with that probe. And so we went ahead and took our measurements in the Superpipe. And indeed, we see that as the Reynolds number goes up, we see the development of this logarithmic region, and it gets longer and longer as the Reynolds number goes up. And that region, in fact, coincides with the same region where we see the logarithmic law in the mean flow. So this is all very satisfying because, you know, this is a key result in the attached eddy model of Townsend and Perry. And it holds this, we show it here for the Superpipe, but it also holds in boundary layers, and it's been shown in other places that it seems to be an almost universal result for wall-bounded, canonical wall-bounded turbulent flows, the same constants. So this was a very satisfying result. Now, we have another expectation about the turbulence, is that near the wall, the turbulence intensity continues to increase with Reynolds number, and that's this inner peak that's been identified on the right. Here we show the same data, the Superpipe data, now in terms of y plus instead of y over delta in a semi-log plot. Now, the first thing was that, again, you know, when you ask questions, you sometimes get surprising answers. And the surprising answer in this case is twofold. One was that we saw the appearance of an outer peak in the turbulence intensity, which was unexpected and certainly not observed before. So that was a bonus. The second part of that is that we didn't see the inner peak grow with Reynolds number. It sort of went up and then it kind of stopped growing. So what was happening here? Well, let's compare that to some other results, and we can show the other results. This is taken from Leon Moser. Again, this plot. It's been, I modified it a little bit, but what you can see there is that there is DNS results on the black line, continuing to go up with Reynolds number. There are these hot wire measurements in the Melbourne tunnel that go up, but there's an offset for some reason. And then here are the Superpipe results that go up and then go down monotonically. So what's going on? Well, so it turns out that even though we have these very small probes, when you get close to the wall, the smallest eddies are very small indeed. And we still have spatial filtering on the NSTAP probes in the Superpipe. So we obviously need to go to a bigger facility, which bigger shear layers. And so we went to Melbourne. And we took measurements in the Melbourne wind tunnel using the NSTAP probes. Now, in the boundary layer thickness, as I said before, it's like 35 centimeters or so in that facility at the high Reynolds numbers. And the probes only at a viscous length scale, the length divided by the viscous length scale of about 3. And that's about the size of the Kolmogorov length scale. So we were confident that there was no spatial filtering in this facility. And then what you see is on the left is that indeed the peak in the turbulence intensity continues to grow monotonically with Reynolds number. You can also just see the start of the development of this outer peak in the flow. Excuse me. But the Reynolds numbers are not really high enough to show that peak more emphatically. So now we can plot the NSTAP results in the Melbourne wind tunnel on this plot of the peak value versus the Reynolds number. And we can see that there is a monotonic semi-log increase in that peak value with Reynolds number. And it agrees very well. Experiments agree very well with the DNS in that respect. So we're pretty confident about that result. Now, it's not growing as fast as it should, according to the attached steady model, but that's something that we need to think about a little more. So thinking about that a little more, why does the inner peak grow with Reynolds number? And what is the scaling in that near wall region? And the question might be, how far can we get analytically? So how about using a Taylor series expansion for a small y plus, small distances from the wall? And so we write down a Taylor series expansion. We look at the behavior as we go very, very close to the wall, and we see that the turbulence intensity is going to go as a constant times y plus squared. Now, to find that constant, fu squared, which is just the mean of B1 squared in that Taylor series expansion, we changed the notation because of other reasons. Fu squared is the constant we're trying to find. We need to go really, really close to the wall, so it's unlikely that we're going to be able to measure that using experiments. So let's use DNS. And we take the channel flow DNS. We've done it for other flows as well, but just to use the channel flow as an example. On the left, we see the turbulence intensity scaled the usual way. And we see the growth in the inner peak and all the features we've seen before. On the right, we're evaluating FU squared. So we know that that's the ratio of U squared plus over Y plus squared near the wall. And we can see that it asymptotes nicely to a constant value as Y plus goes to ever small values. So, all right, now that we have that constant, what do we do with it? Well, we can take the turbulence intensity, the scaling we see on the left, and let's divide it by this constant Fu squared that was evaluated at the wall. And I'll call that F scaling. And what we see is a collapse of the turbulence intensity in the near wall region for a Y plus of about 20. And that includes the peak that we've been observing. So there's a connection between the behavior at the wall, where Fu squared was evaluated, and this region, certainly up to a Y plus of 20. It's all scaling in the same way. So that's telling us something. If we take that same F scaling and apply it to the experimental data that we had from the Melbourne boundary layer tunnel, the boundary layer experiment with the NSTAP probes, and we apply that F scaling, then we see it also collapses this much higher Reynolds number result over the full range of Reynolds numbers rather impressively. And one could argue that this scaling actually now goes out to about a Y plus of 50 or so. So it really does capture that entire inner region of the boundary layer, that scale. It's all being controlled by whatever is occurring at the wall. So, and of course, it seems to be occurring everywhere. So what does it mean? Well, if we look at what FU squared actually is, it's the mean square of the instantaneous velocity gradient at the wall. And I can write that in terms of the fluctuating shear stress at the wall divided by the wall stress at the mean value of the wall stress at the wall. So if we look at the scale decomposition of FU squared, which is in this on the left here, we have the blue curve is how FU squared varies with Reynolds number. And then we look at the contribution to FU squared for wavelengths less than 1,000, lambda plus less than 1,000. And we see that's the contribution to what we might call the small scales. And so the small scale contribution is more or less constant as we go up with Reynolds number. And FU squared grows because it has an increasing large scale contribution. So this is now the interaction between the large scales in the outer flow and the small scales near the wall. And this modulation and superimposition of the near wall motions by the large out scale motions was really first developed by Ivan Marusic and his group in 2010. And it's been of intense interest since that time. And here we see that this kind of modulation and superimposition by large-scale contributions is what's causing FU squared to grow. And by implication, of course, this is the entire inner region, including the peak, is growing at this rate. So it's all determined by this modulation and interaction. So if I want to just summarize what I've said about Reynolds number scaling, it's clear that experiment and computation have revealed many new aspects of wall-bounded flows. We've seen the sort of restrictions that apply to the mean flow log law, the fact that there is a power law that is interposed between the near wall region and the start of the power law, that there is a turbulence log law for the streamwise turbulence intensity. That's been established now at a high Reynolds number. The growth of an outer peak, which is an unexpected result, the inner peak scaling is if you're careful enough and do the right measurements, you actually confirm the results that were expected before. But it's very clear that we need a Reynolds number greater than 10,000 before we start seeing high Reynolds number behavior. And really up until now, experiments were the only way to get high Reynolds numbers. But it's clear that DNS is coming along very quickly. I've got a plot on the right of how the maximum Reynolds number of channel flow DNS has grown with time. And you can see that, we started at about 180 in 1985. And we are now, just in this year, 2020, 2021, we are expecting to see the RE plus of 10,000 coming on, and hasn't been published yet, but I've seen references to it from Martin Oberlach's group. And so we can expect to see DNS at the channel flow of 10,000 this year. And that might actually tell us what the value of kappa is in a channel flow. So I'm looking forward to seeing those results. Now, I want to change gear for the last bit of this talk away from Reynolds number scaling and to talk about Mach number scaling. So experiments in supersonic and hypersonic flow are often very difficult. If you can think of all the difficulties that you see in a subsonic flow, you can sort of 10 times worse in high Mach number flows. And so let's take a look. Just as an introduction to what the mean flow looks like in a high-speed boundary layer, I have some results from Watson et al. At a Mach 10 flow in helium. And if you look at the mean velocity profile, that's the blue U over U infinity, you can see it kind of looks like a turbulent boundary layer in a subsonic flow. It isn't quite the same thing, but it certainly looks, superficially it looks like it. But while that's going on, if we look at the temperature profile, you can see that that's increasing by about a factor of 30 or more across this boundary layer. So there are enormous temperature differences. And since the pressure is relatively constant across the boundary layer, this means that the density is also changing by the same amount. So there are enormous changes of density across this boundary layer. And we certainly need to account for those density changes, either in some way. They may have important dynamic effects. Let's see. So going back to posing questions again, what did we know or expect to see or have some notion of for compressible flows? Well, one of the things we know pretty well is that the Van Dries transformation collapses the mean velocity profile onto the incompressible form. What is the Van Dries transformation? Well, it's if we suppose that we have an overlap region between the inner and outer scaling in supersonic flows, we'll have a log law. And in this case, we look at the velocity gradient in that region, in the overlap region, and that looks very similar to what we had before in incompressible flows, but the difference is that the friction velocity, or that tau W over rho, now uses the local density instead of the wall density. And so the Van Dries transformation is the integral of that velocity gradient, taking account of the fact that the density is varying. And here it's expressed as a temperature ratio because, as I said, the pressure is constant, so that works out fine. So that Van Dries transform velocity can also be written as the integral of U over U star, where U star is now a different friction velocity scale that takes account of the density variation in the boundary layer. So U star is actually varying with distance from the wall. So on the right, you can see the nice result. This is a Mach 7.5 turbulent boundary layer taken by Owen Williams. And when you go from classic scaling, which is the U tau scaling, you can see it falls well below the classic log law. But using the Van Dries scaling, U star, it pops up and collapses very nicely onto the log law. So it's very satisfying. The wake behavior is still varying because the Reynolds numbers are different between those three cases shown here. So that's rather satisfying. Everything seems to be working at a Mach number of 7.5. Now, what about the structure of the boundary layer itself? One of the things that we have learned or think we know about high-speed boundary layers is that the dynamic effects of the density variations are small. Anything to do with the density fluctuation and the momentum variations due to that turn out to be small in wall-bounded flows. And it's really the mean density that is the primary effect on the boundary layer. And to sort of illustrate this superficially is that here show some visualizations. On the top right, we see Mie scattering from acetone droplets that have been introduced well upstream in the boundary layer. This is a Mach 2.8 flow. You can also see the smoke flow visualization by Bob Falco at a Mach number of 0. And you can see the same features in those two flows. It would be, if I didn't tell you what the Mach number was, it would be hard to know the difference. Yeah. You can tell it's a different Reynolds number because there are more scale variations in the supersonic flow, compared to the one in the subsonic flow. There's more fine-grained structure in the supersonic flow. I also show some filtered Rayleigh scattering pictures. These are the colored ones by Mike Smith. And he shows a side view and a plan view. And I've always liked these pictures because the plan view looks like clouds on a summer afternoon when the sun is setting. That's just a beautiful picture. This is a cross section through the flow, and you can see the intermittency of the boundary layer very clearly. So superficially, turbulent structure looks the same as in subsonic flow. What about quantitatively? Well, Morkoven suggested that the turbulent stress in a boundary layer can be collapsed onto the incompressible behavior if we use the local stress as the scaling parameter. And this is the same idea that was under the Van Dries transformation. Instead of using U tau as the velocity scale defined on the density at the wall, we use U star, which is defined using the local density. Now, how does that affect the results? On the right, there's some early results by Kistler using a whole wire, here is shown in classic scaling. And as you go from a Mach number of 0, which is kind of Klebanov result, to a Mach number of 4.7, you can see the turbulence intensity, or here is it's the RMS value. Supersonic flows always use the RMS value because the scatter in the data is much larger than it is in subsonic flow. In any case, classic scaling shows that this turbulence intensity decreases with Mach number. All right. If I take that and now use the Morkoven scaling, in other words, using U star, you can see the data actually collapses pretty well on the Klebanov data in a Mach number of 0. So that's very encouraging. Now, near the wall, turbulence measurements in supersonic flow are always a problem. So we should just ignore that basically and just look at this outer region. So that's very encouraging, right? Okay, now let's look at all the data that's available. And we go from a Mach number of 0 here to a Mach number of 11. And you can see that going from classic scaling to Morkoven scaling maybe improves things a little bit, but it's hard to be really conclusive about anything. And it's because the measurements in turbulence in supersonic flows are just really hard to make. Often inadequate frequency response, so it's sensitive to temperature and velocity, and these shear layers are usually rather thin, so you've got inadequate spatial resolution. So what we decided to do was to use PIV at high Mach number instead. And so here we have a typical PIV setup. You have to, you illuminate a particle-laden flow with a laser sheet. You take 2 pictures, you correlate them, and you can get a direct measure of the velocity in 2 dimensions, but the particles need to follow the flow. And that's a problem if you're in a hypersonic wind tunnel like ours. Mach 8 wind tunnel, the velocity is more than 1 kilometer per second. You've got high temperatures to deal with, and so it's a real problem. But it's going to solve, this was also solved by Owen Williams by modeling the particle response. You have to include inertia, compressibility, and even slip, because at these high Mach numbers, continuum effects become important as well. So you have to be really careful about using PIV at high Mach number. But here's the result. So for example, on the turbulence intensity, on the left, we show some instantaneous views. That's just really, colored fluid dynamics. So, but you can see the kind of structure of the boundary layer. But on the right, quantitatively, we see that indeed Morkoven scaling does collapse the boundary layer more or less only in the outer region. There's still an effect of increasing Reynolds number near the wall, but the agreement at matched Reynolds numbers with DNS, that's the circles with the solid black line, is very satisfying. So we seem to be getting some good results for that. So results agree with DNS at the same Reynolds number. They show the expected behavior with increasing Reynolds number, and those support more Corbin scaling. However, when we look at the wall normal component and the shear stress, we don't get any collapse of the data onto the expected curve. So, well, it turns out that it's just really difficult to measure the wall normal component. And this is a general result for all experimental methods and almost all experiments. So it's really, really difficult to get the wall normal component right. So what do we do? Well, this is about the last result I wanted to show you. And what it is DNS done by Pino Martin in 2011. So it's been around for a while. It's in a relatively small box, but it's at matched Reynolds numbers, more or less. And the Mach number range is from 0.3 to 12. And for all three components of the turbulence, Corbin scaling collapses the data. So this is very impressive. The bigger box results are coming soon, but and they're basically going to confirm the same result. So Corbin scaling using DNS works for all turbulence components. Now, originally at 2011, these DNS work was validated using experiment. And now we're in the opposite case. We're validating our experiments using DNS. Big difference. So let me summarize what I've been talking about today. It's obvious that fundamental studies of turbulence must be performed as a partnership between experiment and DNS. So some questions can still only be answered by experiment. Some questions can only be answered by DNS. But for canonical wall-bounded flows, DNS very soon will be at the kind of Reynolds numbers that we need to understand high Reynolds number behavior. And of course, once we have access to DNS at those kinds of Reynolds numbers, we probably don't need to do as many experiments as we've been doing, because now we can probe the flow in wonderful and exciting detail. So experiments are obviously going to continue to be important, because as soon as you depart from canonical flows, there's a whole spectrum, a whole wide world of new things that you can look at. And this is often much more conveniently done in experiment than it is by DNS. So the wide world of experiment is really turning away from canonical flows to look at these more interesting non-canonical flows, if you like. And of course, at high Mach number, what's happening there? Well, when you add heat transfer or reacting flows or chemistry or ablation or anything like that to these high Mach number, these hypersonic flows, real hypersonic flows like you might get on a vehicle, experiments again become almost impossible. They're already difficult in a canonical setting. They become almost impossible when you add chemistry. And so I think where we'll see DNS essentially taking over to do that kind of fundamental study of these very complex flows. And as I said before, in 2011, the high Mach number DNS was validated using experiments, and in 2021, high Mach number experiments are validated by DNS. So we've really seen a sea change in how computation and experiments work together. So I will, I will leave you with this. I call this the ascent of fluid mechanics. It was a cartoon that Tony Perry drew, I think around 1980, maybe 1981 or two. And you can see as you go from left to right, we start with the brain, and then the brain on fluid mechanics is propped up by experiment theory and numerics. And you can see the slide rule as there's the symbol of the numerics. And then as we go along, we still have experiment and theory, but the numerics is supported by CFD. And this is in 1980, mind you. The last one says that computers are embedded in experiment, embedded in theory, to support the brain working on fluid mechanics. So I came across this cartoon recently, and I couldn't help thinking how perspicacious Tony was in anticipating the kind of place where we're at right now. So thank you very much.
Okay, let me thank you on behalf of everybody for a very stimulating talk. Are you okay to answer questions?
Yeah, sure.
Okay. Okay, so if anybody wants to ask a question, if you could raise your hand virtually. Kath, do you want to go ahead?
Oh, sorry, that was the clapping.
Oh, sorry.
Oh, that was a clapping.
That was a fantastic talk, though. And I really, yeah, I'm pretty new to Melbourne, so it was fantastic to just see the history of what's been happening in this place. Thanks.
Thank you. It's kind of a fun thing to look back and to see, you know, even in the last 10 years, how much progress has been made, and I think it's going to get very exciting soon, because, you know, we're going to have access to incredible detail of information, and it's going to be we're actually going to be able to tell you what the value of kappa is soon. I mean, I know Philippe Spillard will be very excited to hear that.
So what is driving the increase with computers? Is it the speed of the processor, or just going massively parallel, which is?
Yeah, I mean, it's a combination of things. Obviously, resources have grown. You know, I mean, what I showed you was a sort of semi-log or logarithmic increase of Reynolds number with time, and that's, you know, kind of Moore's law for DNS.
Yeah.
So it's driven by the computer resources. But they've also made enormous strides in these algorithms that they're using. So, you know, there's always that algorithm development at the same time as having the resource availability.
Yeah. There is a question in the chat window, if you can look in the chat window. So down on the bottom of the page.
Yes, here. Regarding the conclusion for adequate Reynolds number, what would it imply for experiments for cases such as rough walls, where the Reynolds number is typically a lot more modest? Oh, this is a very good point. Yes, obviously, if you have a fully rough flow, then the wall friction, the skin friction, is independent of Reynolds number, right? So at that point, Reynolds number is not really the problem. And so once you've achieved fully rough behavior, a modest Reynolds number is just as good as a very high Reynolds number. And so, you know, and in fact, it's been suggested at various times that you could learn a lot about very high Reynolds number flow by looking at rough walls, not too close to the wall, of course, but in the outer region. So yes, you know, that's definitely true. If you're in a transitionally rough regime, somewhere between smooth and fully rough, then of course the Reynolds number is going to be important. And so you will just need to, you know, if you're interested in high Reynolds number flows, you're just going to have to put them in, you know, rough walls at high Reynolds number, and not be satisfied with modest Reynolds numbers.
I think Sally Tanvir has a question.
Yes, can you hear me?
Yes, I can.
Oh, okay. I haven't been following this, but years back, I think Barenblatt and someone else, I can't remember. They had raised this claiming that there was no such log layer, or, you know, they had some alternate explanation. Yeah. So I wonder if what is the status of that claim, and if experiments can be done to figure out what their claim is, whether they're right or wrong, or we don't know.
Yeah. The important thing to note about the Barenblatt power law was that there are two constants, the multiplicative constant and the exponent. Both of those constants were varied with Reynolds number.
Mm-hmm.
So you can fit a lot of data when you have two constants that you can vary independently. The power law that I described has constants independent of Reynolds number, and that power law only describes the region up until the beginning of the log law. And differences between log laws and power laws are sometimes very hard to distinguish. There is a great deal of somewhat perhaps sentimental attachment to the log law, and I am very attached to the log law myself. And so unless a better explanation comes along, we tend to just go with the log law. And Barenblatt's power law, Barenblatt and Chorin were responsible for that. Because they have these constants that vary with Reynolds number, it wasn't clear to me and a lot of other people what exactly they were bringing to the table. What's better about this than the log law? As I said, you can always take data and fit power laws to it if you let the constants vary. Now, if you wanted to set up an experiment to look at that issue, I think we already have the data. They used Nicorazzi's pipe flow data for their theory. They didn't like the data from the Superpipe because they said it was affected by roughness. I then spent 5 years proving them that the roughness wasn't an issue, but we haven't really ever closed the loop. They never went back and used our data because it actually doesn't agree with the results they got from the Nicorazzi data. So in some sense, we need to close the loop. I don't think we need more data.
Mm-hmm. Thank you.
Question from Doug Smith.
Hi, Alex.
Hey.
So going back to the scaling of the subsonic flows, so near the wall, with that scaling that you've come up with, so it's clear that you're showing that it's very near the wall, it's self-similar, right? So everything collapses nicely with Reynolds number. But if I understood sort of how your F sub U squared sort of changes and the impact, it would seem that as the Reynolds number goes up, the impact of the outer scales on that near wall region grows.
Yes.
Is that correct?
Yes,
so,
absolutely.
But yet the similarity sort of is retained.
That's right.
Right. So there's an impact, I guess. Is that counterintuitive, or is that does that make sense that even as the sort of scales that are impacting that turbulence intensity and that very near wall region are changing, that the similarity still is retained?
Yeah. Now, there are two pieces to this, right? There's the fact that the data collapses, and the conclusion from that is that whatever the outer scales are doing, they're doing it to that whole region. Somewhere from 0 to a y plus of 20 or 30 or 40, that whole region is being affected in the same way by the outer scales, right? Because the data collapse that way.
Right.
Now, the second question is, as we change the Reynolds number, that outer contribution is obviously increasing, and therefore FU squared is also increasing with Reynolds number. The precise mechanism of that, of course, it's we can describe it, but I think we don't really have a good explanation, or we have an explanation. What we don't have is that we don't have a quantitative assessment of that interaction. A predictive assessment of that interaction. Is that okay?
Yeah.
Yeah.
You're asking me if that's okay?
No. Anyway.
You're the expert.
Good to hear from you, Doug, anyway.
Yeah, nice to see that. Good talk, Lex. Very good.
Thank you.
Do we have any more questions? Okay, well, we leave the meeting room open usually for 5-10 minutes if anyone wants to ask any questions afterwards. But meanwhile, let me thank Alex for a really excellent talk. Thanks, Alex.
Thank you, Phil. Thank you for the invitation. It was a pleasure.